and then the class is recorded. Okay, so any of you, please help me with this definition. So solution of algebraic and transcendental equation. What's an algebraic equation? What's an algebraic equation? Could anyone help me to define this? Very easy, it doesn't have to be tough. I mean, I just want an easy definition. Something very easy, an algebraic equation. So what do you understand by algebraic equation? I'm pretty sure that you know what's an algebraic equation, but you just don't want to participate probably.
Es una operación con variables y que tiene algunos coeficientes.
Oh, yes, of course, but that could be also a transcendental equation. So if we are actually more specific, so an algebraic equation, it's an equation in form of a polynomial. So that's it. Remember, we actually discussed what a polynomial was in the previous class. So in this case, an algebraic equation is just what? It's just a polynomial. That's what it is. I mean, we can define it very difficult. We can define it very, like specific. But in easy words, it's a polynomial. So, and of course, what's a transcendental equation? What would be the definition of a transcendental equation? What do you think? What's a transcendental equation? Una ecuación trascendental. So what do you think that is? We already know the algebraic form. So what do you think that is? So it's actually, oh, who wants to participate? Montoya, you want to participate?
Creo que son funciones cuyo valor no se obtiene con el valor de una variable.
Good try. I mean, it could be, but in general, when I say that it's actually transcendental, we're talking about a function that contains other functions such as exponential functions, logarithmic functions, or just like trigonometric functions, or any other type of functions inside of itself. For example, I would say like exponential of x squared plus 2 is actually a transcendental, even though it has a polynomial inside of the exponential. The exponential is a function in general, so it's a transcendental equation by itself. So in this chapter, we will discuss actually some of the numerical methods to solve algebraic and transcendental equations. For example, the equation fx equal to 0, where fx is any of these type of equations, either algebraic or transcendental. But we said that it's algebraic when fx, it's purely polynomial in x. Not only in x, could be in y, but in this case, because we're defining fx, so it's purely polynomial in x. Okay? If we actually analyze these examples, so this is purely polynomial. So there are only, like constant x to a certain degree, and then it's a polynomial of third order, right? This is a polynomial of fourth order, so this is purely polynomial, okay? So in general, if we say that fx contains some other functions, as I said, could be trigonometric, logarithmic, exponential, etc. So the equation fx equal to 0, it's called to be transcendental equation, okay? So remember that you want to have all these slides in Eminus. I'm going to upload them today, so don't worry about like writing down. It's fine if you want to write it because you get more information later. But just to let you know that you don't have to type anything. I would like for you to participate in this class. Okay, so examples of the transcendental equations. So here we have 3 examples. So we have 3 times the tangent of 3x. So no matter you have this 3x here, you have a function which is tangent. So in this case, you have on the right-hand side of the equation, you have a 3x plus 1, which is a polynomial, but you still have what? You still have these 3 tangent of 3x. So you have a function here. So this is an example of a transcendental. Same here, we have x minus 2 times sinus of x equal to 0. So because you have the sinus, a trigonometric function, so you can say that this is a transcendental equation. Okay, and finally, exponential to the power x equal to 4x is another example of a transcendental equation because you have exponential function in one of the sides of the equations. In this case, the left-hand side. Okay, so these are examples of both of algebraic and transcendental equations. Okay, so but now moving forward in this topic, because we want to extract the solution of these polynomials, we want to calculate the solution, so we need to know what is called a root. A root is actually una raíz. No es una raíz de una planta, es una raíz numérica, por supuesto, ¿no? So a root, in this case, it's actually symbolized by the number alpha. Alpha is called a root, okay? And it could be actually any number, even 0, that provides actually that the function fx is equal to 0. So any x value or any alpha value evaluated in the fx equal to 0, and if this reaches the right-hand side of the equation, a result, so it's going to be equal to a root. So this alpha value has to satisfy this expression, fx equal to 0. If only, of course, here you have actually this part, f of alpha equal to 0, and geometrically, this is important. Geometrically, it's a real root of the equation fx equal to 0 if the value x, where the function fx meets the x-axis in the rectangular coordinate system. So for those that are interested in, you know, like what's a rectangular coordinate system, it's what we just call the plano cartesiano, the Eulerian coordinate system, okay? So we actually have an y and x, and we find the solution of any function when the function by itself actually intersects the x-axis, okay? Do you have any question about this definition?
No, profe.
No? Okay. So remember, this is very important for you. There is going to be an exception, but we're going to see this exception later on in this chapter. But in general, remember, a root, alpha, it's called a real root if only f evaluated in alpha is equal to 0, numerically. But also, geometrically, it's a real root when the value in x intersects what? The x-axis in the rectangular coordinate system. So that's what we want to do. So for example, if we assume any function is here, any function here, fx equal to 0. So we are saying, or we are assuming that this function has isolated roots. So what do I mean by isolated roots? I mean that we have actually a neighborhood. When I say a neighborhood, it means I have an interval between A and B where the solution by itself can be found. Okay? For example, I don't know if I actually can see, I want to use the whiteboard. Let me just change to the whiteboard real quickly. So we have the board here. And I'm gonna present this. So here you have, this is the x and y, and then you will have any function. This is the function fx. So here, exactly, you have the root, because this is the intersection with the x-axis. So here you have actually the root alpha, right? Alpha is here. The x value, it's equal to alpha. So that alpha evaluated in the function f, oops, is going to be equal to, sorry about the drawing, is not the perfect one. So let's just actually, let's just erase this one because I don't like it. So let's just use alpha. So let's just use it like this. You already know that alpha is this one, right? So this is the function I have to do. So when I say neighborhood, so if we want to study the neighborhood of a function, I have one here and then I want one here, and then I'm going to say that this is the neighborhood. This is the value of A right here, and this is the value of B. So B is here. So this is what I call a neighborhood. Neighborhood. So this is what I call a neighborhood. So this is in general, it's what I want to, select when I want to find a solution for this equation. So I have to select always a neighborhood. Even for the methods that we're going to see later, we're going to select a neighborhood to actually find the equation. Okay, so I'm going to just go back to the presentation. So, and then I have the presentation here. Oops, sorry. Let me just put this, over here. So we have, the neighborhood defined, and the neighborhood has to contain only one root. Okay, only one root. It couldn't actually contain two roots. We are assuming this. Okay, so approximately the isolated roots of the equation 1 has two stages. Okay, isolating the roots, that is finding the smaller possible interval A and B. So the smaller, the better. Why? Because we're going to be able to see the solution geometrically and numerically. Okay, so it also, this AB has to contain one and only one root of the equation 1. So it's important that the neighborhood A and B contain only one root. Someone can tell me, Professor, but what about if I want to find more roots? When I want to find more roots, I have to select two neighborhoods. So I'm going to extract first the one of the roots, and then I'm going to calculate another root. So I just have to identify different neighborhoods. Okay, so improving the values of the approximate roots to the specific degree of the accuracy. Now we state a very useful mathematical analysis without proof. So what we're going to do, of course, is that we actually have the plot of the function. So what we are going to do is with our eyes, just visually, we're going to say, okay, this value, this graph or this line intersects the y-axis at this point. Okay, at this point, I would say like it's 2.5. So by eye, just using your eyes, visually, you will identify the root. Okay. However, someone can ask me, Professor, but this is kind of difficult, right? Why? Because if you actually plot the function, you'll see that the function can actually have a lot of, roots. Or even if you select a neighborhood, so probably the root is not inside of the neighborhood. How can I tell that the root is inside of this neighborhood? That's a very good question. Why? Because if I select the neighborhood, going back to what I just shared. So for example, if I go back to the board, let me just get this loaded. So I could say something like this. So let's just draw another one. So I have this one and I have this one, right? So and someone tell me, Professor, I want to obtain the root of this. So how many roots I have here? Of course, I have two roots. I have one root here, and I have one root here. And in general, if you think about it, you will have one neighborhood here. I'm just going to use this to actually one neighborhood here, and then one neighborhood here. So you have two neighborhoods. So this is, but what about if you select something in between? For example, let's select this value, this range. You will see that you won't be able to find the root. So this is kind of difficult for complex equations. So, but why numerically can actually provide an evidence that I have a root inside of my neighborhood? So this is what we are gonna do right now. So going back to the screen, so we have something very important. So if we actually want to find if the root is inside of the neighborhood I selected, what I have to do then is just to actually evaluate my function in the neighborhood interval. So I have to evaluate my function in A and evaluate my function in B. So if I evaluate these values, these intervals in this function, and then I multiply both of them, this has to be less than 0 to indicate that the interval will contain at least one root of the equation fx equal to 0. In other words, there will be at least one root if c, which c is equal to the root, belongs or is inside of the interval a and b. Okay? Do you have any question about this concept? Did you get it?
Entonces, la multiplicación de la función de A por la función de B tiene que ser menor que 0 para estar seguros que es donde se encuentra el 0, ¿no? Donde
Exactly. You said it right.
Donde X es 0, ¿no? Ah, ok, perfecto. No, sí, ya.
Great. That's actually a very good explanation in Spanish. Thank you so much for the help. So, anyone, questions? No? So it's clear. Thank you very much for the contribution, Calderon. Okay, so let's continue with this. So for example, let's use this assumption here. So we have also some other assumptions. First of all, we have to say, or we have to assume that fx is continuous and continuously differentiable up to sufficient number of times. Okay, so one of the assumption is that this is always continuous. Okay, there is no gaps in between. They are not actually cutting off the function. It's always continuous in the interval a and b. This is very important. Additionally, fx0 has no multiple roots. So inside the interval, you only find one root. One root, okay? So in this case, the root is going to be equal to c right here. Okay, so fc evaluated is going to be equal to 0, right? Because in this case, y is equal to 0. Okay, so and additionally, if I compute the derivative of this function has to be less than 0. Because we don't want actually a flat line, we want a line with the slope. And then, well, it could be also greater than 0, of course, could be less or greater than 0, but it cannot be 0 inside of the interval. Okay, so it could be actually a positive or negative, a negative or positive slope of the function inside of the a and b neighborhood, but it cannot be 0. So for example, in this figure, so you have this neighborhood A and B, and then this is FA or F evaluated in A, it's right here in this point. And then you have F evaluated in B at this point here. And then you have the plot. and you see that you only have one intersection where x is equal to c, and if you use this value x equal to c in the function, you'll see that this is going to be approximately equal to 0. Why I say that approximately equal to 0? Because, of course, visually it's very difficult to establish a very good accuracy of the solution. For example, if we're going to do some examples, if we have examples with, you know, like decimal numbers, so you'll see that this could be actually 2.1, but in reality, the solution could be equal to 2.125. So a better approximation, but because your eyes are limited, so we just say that it's 2.1. So just be aware that it's an approximation. It doesn't have to be the real solution. So let's continue with that one. So let's start with the first method. This is the first method, actually. Okay, so this is going to be officially the first method we're using to actually compute the roots of the equation. Again, we are assuming that we have a function x equal to 0. Okay, and the real root can be determined approximately at the abscissas of the point of the intersection of the graph of the function y equal to fx with the x-axis. I already told you that the solution, it's what? It's where the function meets the x-axis, or where the function intersects the x-axis. Okay? If fx is very simple, we can just draw the graph of y equal to fx with respect to any rectangular axis x prime 0x or y prime 0y. So this is just a rectangular uncommon rectangular coordinate system. So it's the one you know. The point at which the graph meets the x-axis are the location of the roots of the function fx equal to 0. However, so there is an exception. There is an exception, especially for the transcendental functions. So if fx is not simple, it means like fx is not actually easy as you expected. We can replace the equation 1, the equation fx, by an equivalent equation. And we can say that in this case, phi x is equal to phi x, where the function phi and phi x are simpler than fx. So it means like if we have a very complex equation, such as, for example, this one could be some complex, this one. If you want to plot this one, it's going to be difficult. Well, you can actually take this to this side, and this is going to be equal to 0, and then you plot it. But in case that we don't want to plot this like that, so we can actually assume that this is the phi and this is the phi equation, right? So we can actually use these two, and then we plot them apart. We plot them separately. So we're going to make one plot of this one, and in the same plot, we're going to do the plot of this one. And then with that, we actually construct the graph of both of them, and then the x-coordinate of the point of intersection between the two plots gives a crude approximation of the real roots of the equation 1. So we have two options if you think about it. The first one is if fx is very simple, you just plot one line. And you get the root by visually obtain the intersection with the x-axis. On the other hand, if fx is equal to a complex function, you can separate the equation into two different functions. The first one is going to be phi x, and the other one is going to be cx. And then you construct or you plot the two lines. So you will have two lines because you're plotting one function, which is phi x, and then phi x. So you will have two lines. And then to find the root of the equation, of the fx equation, you have to actually calculate the value of x where the plots or the graphs or the lines meets or intersects. Okay, so that's what you do to obtain the roots. Do you have any questions for this?
Profe, en este caso, si separamos las dos ecuaciones, tendríamos dos raíces.
No, only one root, because your root is where the two equations actually intersect. Okay, we're gonna do some exercises. Don't worry, in a minute to actually do some plotting. But do you have any more questions about this? No, everything is clear. Man, I have very good students. I'm so proud of you. Okay, let's continue. So, for example, this is one of those examples that I want to discuss. For example, this, you have x log base 10 of x equal to 1. Even though this is not a very complex function, I can actually pick this function to actually go and separate it in two different functions. So I take this x to the right-hand side of my equation, and it's going to be 1 divided by x, right? So then if y, I have one function here, y divided by x, so this is going to be one function, one line that I'm plotting for this side, and then log base 10 of x is going to be my other function. And then now the root is going to be where these two intersects. So the intersection, which is actually about 2 point something, 2.1, 2.2, something like this. So it's the solution of the equation.
Ah, ya me quedó más claro. Entonces, el punto en el que se intersectan las dos gráficas es el punto en el x va a ser la solución, ¿no?
Exactly. So this is the case when you separate the function, when you have a complex function. Thank you very much. You would be a good professor, by the way. So let's continue with the class. So now it's time to actually go and see Matlab, okay? Because we are not plotting this by hand, because if you plot this by hand, it's going to take you probably 1 hour of the class. So we don't want to do this by hand, because if not, you have to go to the papeleria and get to papel milimétrico, and then you have to use rulers and things like that, and that takes a lot of time. So, but in this case, we're going to actually use Matlab, and of course, Matlab is not only a program or software to just plot function. It's actually more complex than that, but we are going to use Matlab for that. So that's why I told you that you have to use Matlab in this class. Okay, let me open Matlab just for that. So Matlab. So you'll see that I'm going to give you a quick review of the Matlab, because probably you don't remember that one and you need to refresh a little bit. Let me just wait a second because it's opening. I'm going to drink my cheap coffee today, Nescafe. So this is Matlab. This is Matlab in general. You probably know Matlab already. So you know that in Matlab you have this interface where you can do some certain operations, 2 + 2, 3 divided by 2, and you can do any multiple operations, right? So you can do many of them. You can actually use a matrix. So a matrix A could be equal to 2 and then 2, 4, and then separate. This is going to be 3 and 7, and then you have a matrix. So this is a matrix 2 by 2. You can compute the inverse of A, and then this is the inverse of A. So that's it. So you have a lot of functions in Matlab. So I'm assuming that you already took the class of Matlab, your basic class of Matlab. So, but now it's time to actually use Matlab for plotting functions. So in general, if we go back to the presentation, so we have to make 2 functions to do this process. So the first process is to actually use this function 1. Well, actually, I documented remember that I like documentation. So documentation, this script provides a graphical solution of a specific function. So I have a mistake here, so it doesn't matter. So author, it's me, right? So, and functions, in this case, my functions are function 1. This is a name, this is only a name, remember. It could be X, it could be whatever you want. So this is my function 1, is gonna be at, which is the arroba, at X, comma, N, with N is equal to the vector of points that I want to evaluate, space, and it's gonna be my first function. If you remember, my first function is equal to log 10, base 10x. So log 10 of x. I put this semicolon just to avoid plotting this part. Function 2 is equal to at x, comma, n, 1 divided by x. If you see here, I have a dot. I don't have just the backslash. But you can tell, Professor, why you have a dot? Because this is a vectorial operation. So I want to actually, have this as a vector of divided by the 1 divided by the vector, or the values that I'm inputting in this case. Okay, so this is the function. So, and then I have to provide the values where the neighborhood, the values where I want to actually plot. My neighborhood it goes from 0.2 to 3.5. So A is equal to 0.2 and B is equal to 3.5, right? So now I have to provide the results of my functions evaluations, right? So I have to give results 1 is equal to the function 1 evaluated in my neighborhood. And then my results 2 is equal to my function evaluated in the neighborhood. My function 2 evaluated in the neighborhood. Okay, and then of course you have options to plot. This is a figure, render, painter, position. So this is just the position of my plot. So this is not relevant for the class. You just can use figure and then type it however you want. So I have a plot. The plot is going to be my neighborhood with my results number 1 with a line width of 2. ¿Cuánto es el espesor de línea? Line width. And then I have to use the function hold on if I want to introduce a second plot in my current plot. So I use the hold on function, and then I plot the neighborhood and the results of my second evaluation with a line width of 2. And I just use the labels in X and Y with X and Y as my characters, and the font size for both of them is going to be 14. And all the axes in my plot is going to be the font size of my axis is going to be equal to 20. Okay, so this is the function, and then this is how I actually plot any type of function in Matlab. So, but let's just go and practice a little bit. So here you have function to clear Matlab. You use CLC, and then if you want to clear the variables, you just use clear, and then CLC again, and everything is in blank. So it's like that. So I have the function here. So this is what I have here. It's exactly the same. As I told you, here you have a function. It's already declared. I have my neighborhood. So this is my neighborhood. Let's just call it here neighborhood or interval A, comma B. Right? In this case, A is equal to 2, for example, and then A is equal to how much? 3. And then if you think about it, I have a space here. I have something here. So this is 2. Can you see it? Because I see that you cannot see it clearly. Do I have to increase the font? ¿Lo pueden ver o incremento la fuente? Porque Creo que están como forzados en la vista.
Sí, sí, está muy pequeñito.
Ok, voy a incrementar un poco la...
De hecho, nosotros podemos ampliarlo.
Sí, profe, eso le iba a decir, podemos hacerle zoom a
Pero
la
se pone
pantalla.
pixeleado, ¿no?
Bueno,
Pues
ok.
no, bueno, sí,
Se
también,
pone
bueno,
más claro, de hecho.
sí, de hecho, sí. No sé si se ve.
Se pone pixeleado.
Okay, don't worry.
Ah,
It's
chat.
okay. It's okay. Don't worry. I'm just gonna change this. We don't want to, like, make a big deal of this. I just use 14. So what about now? Can you see it better?
Sí, profe.
Okay. So as I told you, you have the function here, function 1, function 2, and then I have my neighborhood 2, start at 2, and finish at 3. However, the increment from 2 to 3 is going to be each 0.1. Sorry, 0.01. Okay, so this is the increment that I have to follow. For example, I'm just going to run this part, and then I'm going to run this one. And if I type XX, so you'll see that my increments start like 2, 2.01, 2.02, 2.03, 2.04, all the way up to 3. So that's the increment. Okay, and then because I have the evaluation, these are the points where I want to evaluate. I just can evaluate the values of my neighborhood inside of the function. So I evaluate both functions. Done. And the results, res1, are here, and results of res2 are here. However, of course, numbers doesn't give me anything, so I have to plot something. So using the plot, as I told you, so I'm going to plot the first line. So the first line is here. This is the first line. And then it doesn't give me anything, right? Because this is not the solution. So I'm going to apply the hold on, and I'm going to apply all the settings. And then look at this. So here you have it. So this is actually the same as this one, but in a zoom. So if you want to actually think about it, so I have the solution. It's about 2.4, 2.5. I would say 2.5, right? A little bit more, but it's here actually. Yeah, 2.51. So it's there. So you can click on that one, and then you have 2.5 there. But it doesn't actually look right. I can actually type it here again. There you go, 2.51. And then the solution, this is the one, 2.51. Okay, so now to prove this solution, I want you to substitute 2.5 in this equation. Sustituyan 2.5 en esta ecuación. Recuerden que es un logaritmo base 10. And it has to be very close to 1. For those that are in the second class, please try to do it, because I'm also, waiting for you. I'm not live, but you have to do it.
Bueno, a mí me da menos 5.149 por 10 a la menos 3.
Profe,
Really? Oh,
a mí me da .99.
okay, yeah, that's 0.99. That's good. So check the way to actually do it. You did it because it could be wrong. So 2.51 times log 10. So you have to use log 10. I don't remember where I have log 10 in my calculator because I don't use it very often. But log 10, let me just check that out. Log of 2.51. And for me, it's actually 1.00318. So this is what I got. So I got the same. This is almost something very close to 1. There is actually an error of 0.003. So for the ones that got 0.99, it's fine. Actually, I don't know if you can see it, but it's here. And no, it's impossible to see, but it's only one, almost one. But whatever. So this is how I plot in Matlab. So if I want to see something very similar to this plot, just to verify that this is the same plot. So if you think about it, they did it from 0.5 to 3. Let's just change the neighborhood. Let's do it for that one. It would be from 0.5 to 3. So I just do it, save it, and if I go to editor, I can run it, and then this is the one, and this is the one. It's exactly the same plot if you say it. So pretty much the same. So, and I got the solution. The solution here is actually looks different, but it's the same plot. So this is how we plot in Matlab.
Profe,
Yes.
en este caso el resultado, ¿cuál sería? 2.5.
Exactly, yeah, because if you substitute 2.51 in the original equation, this is original, you get 1, right?
Okay.
2.5 es la solución, ¿no? Para que, donde es la raíz,
2.51.
toca
Exactly.
0 en las X, ¿no?
No, it's not 0 in the X's. In the X values, actually, if you go and do it again, it's not 0 in the X-axis. No, it's not even close to 0. It's actually here. So the X value here is 2.51. So if you want to, if you want to intersect the value, it's actually intersection should be here. So be aware of that, okay? So it's not the same. So this is the graphical solution. Let's just actually add a little bit more. You want to do something, I want to actually show you something different because it's important for you to be clear. So the question of your Calderon actually was, Professor, but you know, why is not intersecting the X-axis, for example? So let's actually do the same thing. So let's create another script just for you to be able to see it. By the way, the video of this class is going to be in my YouTube channel. Please, if you subscribe to my YouTube channel, you just watch the video and put a like. No, no, just if you want to actually watch the video, don't worry. I'm going to create a new script. So I'm going to plot it here and I'm going to save it. And it's going to be the same name, graphical solution. Graphical solution. Let me just find this one. Graphical solution, and I'm going to just give it the name. So he told me, Professor, I want you to show me how to do it with the separation, because here I separated the function, but we can actually do it without separating the function. We can go and do this without any separation. So what I do is just do x times minus 1. And then this is the function. Is this function the same? Yes, right, because it's equal to 0. I just took actually x times log base 10 of x, and then I just put this on the left side of the equation, and it's equivalent. It's the same thing, right? It's equal to 0. I just make it equal to 0. So now what I'm going to do is just to eliminate this one because I don't need this one. I don't need this one. And I'm guessing that if my solution is right, whoa, what's going on? Oh, I think it's because of this. There you go. So here you see that it's not touching actually. Well, it's touching the x-axis. Yes, it's here. So it's kind of difficult to see it because the x-axis is here, right? It's here. So when y is equal to 0, you have 2.52. It's almost the same thing that I gave you, right? So you see the x-axis is here. is in 0, right? The x-axis, the 0 here is here. So this is the intersection with the x-axis.
Esto es lo que yo quise decir cuando es 2.5 en X, pero 0 en Y, ¿no?
Exactly. So now you see that we can do it actually both ways. We can do it without any separation, making the equation equal to 0, and you can actually do it by separating the functions. It depends on how difficult your problem is. That's only what you have to decide. If the problem is very difficult, you can do some more adjustment. Okay.
Sí, perfecto. Gracias.
Yeah. For example, here. No, this is not the one. Hold on. I have, for example, I think I have it here. So the next thing that you have to do, this is your assignment. So you already had, that's the first assignment. So now you have this assignment. You have to solve all these equations graphically. Okay? This is your assignment. So for example, I'm gonna solve this one in Matlab just to show you this one. Okay? So I'm using minus minus exponential to the power 2x plus 2x plus 0.1. So this is the exercise number 2, this one. So I can separate the function. So I can actually separate this one. I can send this one to here or send this one to here. So this one is going to be positive if I send it here. So I have the two functions here, and I want to evaluate it in this range. It's minus 0.01 to 0. Let's just make it to 1. This is going to be from minus 1 to 1. So this is my neighborhood, minus 1 to 1. I want the results, of course, of the function, and I want to plot it. So I'll do it, and I want to run it, and then, ta-da! So this is, oops, is not actually touching. There's no touching. So what's going on there? So let's just try to find another route. Just extend. Let's just do it to minus 5 to 5. So what happened, right? Minus 5 to 5. So this is crazy, right? So I think it's, sorry, I have to run this separately because I have another thing. So this is the one. And you could say, oh, professor, it looks like it touches. It's touching. Yes, it's touching here, right? Probably. I don't know. It doesn't look like it's touching, right? Because I put here, this one is not touching yet either. So here, oops, here, it's not 0. So it's not actually, the value that I was expecting, the intersection. So I have to play with the intersection. So 0.01 and then 0.1. So this is the minimum amount that I can actually zoom in. So you see that it's not touching. So for this equation, specifically in the case of number 2, there is no graphical solution. It could be also a problem. So it doesn't don't get afraid of saying, Professor, I didn't find the solution because they are not touching. So in this case, they are not touching. So there is no intersection. But we can actually do the case of, okay, let's just verify this in a second way. So instead of just separating the function right here, I'm going to make it actually the entire function again. So I just type the equation, I do it, and then run it. So this is the one. So the x value, the x-axis, you see, where is the 0 value here? It's actually on the top here, right? It's here. So it's not even touching. So never touches the x-axis because it's actually like kind of a parabola. Here, But it's not touching the x-axis because it's minus 0.09. So it has to be 0. So this is something very important because this equation doesn't have graphical solution because it doesn't touch the axis. So you have to be careful with your assignment because it doesn't mean that all of these are going to have solution or real solutions. Okay? Any questions before we finish the class?
Sí, yo tengo una duda.
Go ahead.
Cuando se tenga que graficarlo, ¿se tienen que tocar para que esté bien o no es necesario?
Lo que decía, no, aquí no hay bien o mal, no estamos en bien o mal, ¿no? Si no se
Ok.
tocan, no quiere decir que esté mal, sino que no hay solución gráfica. O no existe solución para esa ecuación.
Ah, ok.
Eso es únicamente, o sea, no estamos diciendo que está bien o está mal. Lo que ustedes me tienen que proveer es suficiente evidencia en su tarea. ¿Qué me van a proveer? La gráfica, por supuesto.
Profe.
Y me van a... Dime.
Era sobre eso. ¿Va a querer las puras capturas, por ejemplo, de cada gráfica o también la codificación? Bueno, el programa.
No, los códigos también los voy a querer, los códigos. Pero, por ejemplo, si yo hago esta gráfica, quiero el código de cada uno, pero el código no me lo tienen que pegar en Word, me tienen que incluir su archivo de Matlab de todos los códigos. Así como dice aquí, mira, por ejemplo, ejercicio 1, ejercicio 2, y así me lo van colocando, solamente me lo separan con algo así.
Ah, ok.
Entonces, para que no haya problema, ¿no? Pero me mandan el archivo de Matlab.
Ah, ya
Entonces,
todos estos puntos de todas estas gráficas en un solo archivo de Matlab, ¿no?
no, bueno, esto en Matlab me lo van a mandar así. Y el archivo de Word, lo que van a hacer es que me van a plotear esto y lo único que hacen aquí en este caso es save as. Y me lo guardan como una figura, por ejemplo, ¿cuáles son las más comunes? PNG, ¿no? Ahí está. Me lo guardan y ¡pum! Le dan guardar. Exacto. Entonces
Claro,
me lo guardan y lo pegan en Word.
Ya le iba a tomar captura.
También se puede, ¿no? Pero a veces la captura sale medio feita, entonces tengan cuidado con eso, ¿no? Tienen que ser claros. Ahora, fíjense bien, mi gráfica se ve claramente los números. Por eso es importante que esto lo consideren siempre en su gráfica, ¿no? Porque miren cómo se ven los números. A veces me entregan unas gráficas que son números chiquititos y no puedo ni ver nada, ¿no? Entonces, sean claros y sean objetivos en su clase. A cada ejercicio le ponen en el archivo de Word, claro, ejercicio número 1, ponen la gráfica y abajo ponen la solución aproximada es igual a tanto. Si no tiene solución, las gráficas no se tocan, por lo que se concluye que no hay solución gráfica. Algo así. It could be in English, it could be in Spanish, don't worry about that. So I won't judge that and I won't take down any points, okay? But you have to be able to be clear in your answers. So you have to include the PDF file with your solution and the code of Matlab, which is actually a file.m. Okay, es un archivo .m que tienen que incluirme con todo el código. Okay? So, and that's it.
Profe, sería la segunda tarea, ¿no?
Exactly. This is the second assignment.
Pues de hecho también le iba a preguntar, igual le comenté a unos compañeros que, bueno, todavía no ha subido la anterior, ¿no? El archivo. Me preguntaba, en qué apartado lo iba a poner. Dijo que en un foro, no, dijo que iba a haber otra actividad, ¿no?
For what?
Sí,
¿Para cuál te refieres?
La anterior. Había dicho que iban a hacer, creo que evaluar unas funciones en...
Sí,
en
unos
el
polinomios, los
Ajá,
polinomios.
ándale.
Oh, no, this is the third assignment, by the way. This is the third assignment, sorry. You're right.
Sí, es
This is
que-
the third one. This is the number 3.
Sí, es que dijo que iba a subir el archivo,
Yeah.
pero nunca lo encontré.
Okay, yeah, I will do so. Don't worry. I will do so, and you will have 1 week to complete all the assignments. Don't worry. Okay?
Sí, porque decía, esta es la segunda, pero la primera todavía no.
No, the first one was actually the infographic. The second one is the polynomial evaluation, and the third one is this one, the graphical solution. You're right. I'm sorry about it. I forgot that one.
Entonces esta sería la tercera.
Yeah. Okay. So Thank you for coming, guys. Thank you for giving me a chance to actually attend my meeting because I have a meeting at 11, so I have to say goodbye. I'm gonna stop recording right now, and for those that are in the second class, so please be aware that this is recorded, and if you have any questions, you can post it in the forum. Thank you very much. Have an excellent day, and I'll see you tomorrow, guys. Have a good one.
Okay.
Bye.
Teacher, see you next class.
Yeah.